Yeah, so I'm Arjun, and I'm going to talk about DynamicAPInt, which is a class for infinite precision arithmetic and LLVM. Of course, it's not literally infinite, but I just wanted to disambiguate between arbitrary precision, which is APInt, which we already have in LLVM, and this one where you don't have to fix the width beforehand, but you can just use as big values as fit in your memory. Okay, so why do we even want this? Well, we have a Presburger library up in MLR upstream. We don't really need to know what exactly a Presburger library is, but basically it's a set of solvers for some types of constraint systems, and it happens to be used in a couple of different places, like for computing bounds of SSA values, or for fine loop fusion, and I've been told in circuit, but there's a couple of places. So it's used in all these places in the compiler, so we want it to be fast and we want it to be correct to avoid miscompiles. So how do we do that? Well, what even is a Presburger library? You don't need to go into the details of the algorithms, but basically what it looks like is you have these matrices and you get integers from them and you do some numerical computations. And what we want is to do these fast and correct. So theoretically, in the worst case, it could turn out that these don't fit in 64 bits. You might need exponentially big integers. But what we found in that paper is that in practice, that's not the case. Most of the time, 98% of the time actually is spent in test cases that can be solved with just 64-bit. So what we really want is an integer class that will be really fast in this case, but just for the sake of correctness, to avoid miscompiles, we just want to have a fallback path for the really rare case where this isn't enough. So like one really simple thing we could do, maybe a little stupid, is like we just like have a class DynamicAPInt, in this case with just a 64-bit integer, and you do a multiply with an overflow check, like with the built-in intrinsic. It'll tell you if there's an overflow. If there is, you just exit, and so the user at least knows that something went wrong without instead of silently miscompiling. But most of the time, you just store the value into x, in this case because it's the because it's the multiply equal to operator, and yeah, and it just works, and it's pretty fast, but it's not really production ready. So what we actually want is something that works at almost as fast as this, ideally, while still being correct. So that's what we want to do with DynamicAPInt. What we're doing is we have arbitrary precision supported just for correctness, but really what we want is for the 64-bit fast part to work well. And how we do that is we basically have a union of an int64 and an APInt. And what happens is we run all these operations on the 64-bit integer in the fast case, and if there ever turns out to be an overflow, then we will fall back to increasingly larger widths of APInts. But that really shouldn't be happening most of the time, and what we really want to focus on is optimizing the 64-bit path. So how do we turn that silly thing we had earlier, which is basically just a performance roofline for us, into like a more like a real solution? So now DynamicAPInt is a union of 64 and APInt, like we said, and we have a tag that tells us which one it is, and yeah. So we just need to check the tag, and then if it is in the fast case with the small 64-bit integer stored, then we do the multiply with overflow, same as before, and yeah, we have to check the overflow flag, and if there was no overflow, then we'll actually store the result and return. And if the fast path doesn't work, then there's some slow path that we don't really need to worry about because it's not going to happen, but we just need to make sure it's correct. It uses APInt. Anyway, how do we make the fast path fast? So we want some kind of benchmark. So here, this is basically a microbenchmark where you just do a lot of multiplies. And this, in this case, is like the roofline because we just have a 64-bit int and exit if there's an overflow. So, of course, like the compiler could optimize the whole thing away. So we need to do a couple of things. We need to use x. And we need to actually take, instead of having 1, because it knows that 1 times 1 is just 1, it's going to optimize the whole thing away, we can take it as input. But let's ignore all of that and assume that we convince the compiler not to get rid of the whole thing. And yeah, so we have this as a sort of roofline, and we compare this against the same thing in our class. So here, we set a dynamic APInt to x and then x to 1, and we keep multiplying it with 1. And similarly assume that we took 1 as input and so on. So when we started trying to optimize this thing, one interesting thing, in the spirit of a student talk, I'm going to tell you some lessons that I at least learned that I thought were interesting, which is that when we started looking at this, we realized that if, depending on how the loop in the top function gets unrolled, the performance of our code could actually change, even though they're completely different functions. But yeah, as it turns out, in Skylake, Intel CPUs, the location of your code actually matters. So depending on where your code ends up in, if your entire critical loop is in like one aligned segment aligned to something, it's going to be slow. And yeah, we found this blog post basically which mentioned this. And so, for now we just switched to an AMD laptop that we had lying around. And yeah, so now how do we continue making this faster? Let me get rid of this thing. Okay, let me just get rid of this thing. But yeah, so how do we now actually make this 64-bit integer class faster? One thing is that we've been saying the whole time about basically that this fast path is going to be taken 98% of the time. And so we should tell the compiler that so it knows to optimize that path. But actually, it turns out that in AMD also you have the same thing with the code layout. And if you annotate some branches with some annotations like this, then you might change the ordering of basic blocks, and you might mess up the alignment, and it might actually become slower, which is what happened in one particular example, even though we annotated it. A branch that was always taken in the benchmark. But yeah, again from the blog post, it turns out that you can pass some arguments to LLVM to align everything appropriately. And then it kind of works, and this makes it about 1.2x faster, putting annotations like this everywhere. And the other thing is to inline. That again has a notable effect. And yeah, now that we added these basic things, we can come back to the microbenchmark, and we looked at this thing. We looked at the assembly that came out, and we played with it for a while. And what we found out is basically, if you look at the microbenchmark after inlining, there's these 3 branches. It's a really tight loop, and there are 3 branches: the if for the flag, the if for the overflow check, and then there's a continue to continue with the loop. And yeah, so like I said, we switched to this AMD thing, and if you again Google for the Zen 4 microarchitecture, you find this crazy diagram, but then if you zoom in, you find out, okay, there's only 2 branch ports. So in this really tight loop, it's hard for it to do 3 branches, and that actually makes a difference. And we did think of some ideas okay, maybe you can combine these 2 branches into one, and at the cost of some other arithmetic compute, but actually the conclusion is that the microbenchmark loses its usefulness at this point. You kind of saturated its utility, because there's no real world code which is literally just jump, store, one multiply, and then a bunch more branch things. In the actual end-to-end benchmark, any further optimizations you do in this micro thingy, you don't have. So what did we end up achieving on the MLI plus burger thing with all these optimizations? So the APInt, just bare APInt, without even having any overflow checks, is actually kind of slow. If you added overflow checks, it would be even slower. But yeah, even if you just have these, it's 1.5x slower than our dynamic APInt, which is fully correct, overflow checked, is actually always works. And the roofline that we had of the checked in 64 is about twice as fast. That looks kind of bad, but actually there is some hope. Although I won't go into the details of that in this talk, because it's not really the topic. But the main thing that we found out is that there are actually still a lot of tight loops where there are a lot of these flag checks occurring of is this in the 64-bit tag, and you can sort of pull all of these things out, and then like the critical code will work much better. And one of the things that we talk about it in the future work part, but basically we want to provide like a function where you can just give it a lambda, and it will do all the checks upfront, and then do your actual computation. And what I want to say is that if you do things like that, then you can get really close, pretty close to the roofline. So this is like 30% slower than the roofline. So, and yeah, I kind of another thing is when you inline everything, maybe it messes up the branch prediction, because even though these branches are supposed to be always taken or always not taken, like in the fast path, maybe you might think because they get actually put into different places in the code when you inline, branch prediction might get confused. But actually, if you compare the checked in 64 with the dynamic thing, although the number of branches increases by a significant amount, like 25-30%, the number of branch misses does not increase actually that much. So that means that it's able to kind of cope with all the extra branching. And then so the question is like, what is something that actually might be causing the worst performance? And one thing where you can see it is in the L1 data cache loads. So they become basically double when you go from in64 to DynamicAPInt. And if you look at the misses, then they also basically double. So basically it means that we're not able to preserve performance at all compared to the roofline. And that's why one of the interesting ideas that might be worth trying later is to use, instead of a 64-bit, if you just had a 32-bit and some other flag, then the two combined can be a pointer in the slow case, and in the fast case you just use the 32-bit small integer, and maybe that's still enough to cover most cases. So that could be something worth trying. And the other one is the lambda that I spoke about earlier. So yeah, that's the end of my talk. Thanks for coming. I'm happy to take any questions.
Thank you. Yeah, any questions?
What's the size of the type? If it's 64 bits and a tag, how does that work?
Yeah, so that's kind of, so initially it was the 64-bit and a union with the APInt, and the APInt is 128. And then if you have a tag on top of that, it's actually 3 times 64. But so right now it's in a state where there is already a tag inside the APInt, and that's being reused. But eventually, so then it's 128. But eventually we would want to keep all the tag business inside APInt and not have to look at it at all from where we are. But that's not how it is right now. But it's 128 to answer your question.
Hi. Just curious, have you tried benchmarking against other libraries like GMP or Boost Multi-Precision?
No, in this, so right now we didn't, but actually in the paper that I showed you in the beginning, we did benchmark this kind of approach against GMP, and GMP is really good when you have big numbers, but here we really almost always have small numbers, and it ends up being slow. Yeah.
Thank you.
All right, I have a final question. So your benchmarking loop, actually one thing that's kind of common is if you have the trip count of the loop, if that's like fixed and there is a relationship between this trip count and the induction variable, right? Then like SCAF can actually infer and hoist the check. So you will see largely different cogen depending on a naive microbenchmark and what you will see in the real world.
Yeah, so actually I did also try it with by taking the trip count as input, and I should probably have put it on the side, but yeah, I mean, the results kind of hold with,
Okay.
with that as input. Yeah. Yeah.
Right. Okay. Thank you so much. And then
Thank you.
to conclude the student talks, do we have the last speaker? Oh yeah, great.